Hi everyone, I am Flavio, postdoc at EPFL, and I'm glad today to talk about my work FISHFUZZ. This is a work in collaboration between the Chinese Academy of Science and IPC, EPFL, and XIVE. So, let me give you a brief introduction on what is fuzzing. So now is a fuzzing session. I assume everybody knows what fuzzing is, but it is important to understand FISHFUZZ later. Here is a scheme that depicts the normal workflow in a generic fuzzer. We have a queue of seeds, which are concrete inputs. These seeds are selected by using some logic, slightly mutated, and then submit into a program. The program runs, executes the seed, and then we have basically two main outcomes. The first one is that the program crashes or exhibits an error. This is our desirable outcome because we want to find bugs in programs, right? Alternatively, the seed might reach and exercise new part of code or new functionality. In this case, we consider the mutated seeds interesting, we save that back to the queue, and again, in the next iteration, we mutate, select, and again and again. Now, given this design, FISHFUZZ work at the seed selection strategy. So this to give a correct contextualization of my work. FISHFUZZ doesn't propose new mutation or new coverage metrics, just propose a new way to select interesting seeds according to the goal of the fuzzer. Now, keep this back in your mind. I will back to this point in few slides. Then, to better understand my work, I have to give you a brief introduction of other type of fuzzer in the field. There are plenty of fuzzer in the community with different goals. The ones we care for the implementation are mainly three. The first one is the one that everybody knows, gray box fuzzer, that basically consider all the code in a program equally important. And they try to mutate and generate inputs in order to reach new coverage, new code in the program, with the hope to find untested code that arise a bug. A step further are directed gray box fuzzer, where usually the developer mark some part of the code, some line of code, as possible buggy. And then there are these design that steer and focus the fuzzer energy toward this specific target set. The use case for direct gray box fuzzer usually is in case you have a patch and you have only a small modification in your program that you want to selectively test. And further step is given by the sanitizer guided fuzzer. In this class of fuzzer, the fuzzer is considered as possible buggy all the sanitizer label introduced by sanitizer. So let's think of ASAN. ASAN introduced some runtime checks for memory access, for user-free, overflow, etc., etc. In this case, the fuzzer automatically find these runtime checks, called sanitizer labels in the program, consider all of them target sets, and then mutate the inputs in order to try to trigger all of these targets independently. Now, let's focus on sanitizer gray box fuzzer. FISHFUZZ falls in this category specifically. The main problem of this class of fuzzer is the size of the target set. Given that all these runtime checks, all these sanitizer labels are possible buggy, the fuzzer has to deal with the huge target set, which means that first you need to understand inside the set what is really important to test and what is not. This is because fuzzing is an optimization problem that tries to find as many bugs as possible in a finite amount of time. The second problem is that we need a metric that tries to reach and trigger any target specifically, and not just going randomly, but focusing on specific targets. The first challenge, so reaching the targets, for a time being, has been the model with the seed target distance. In this way, the fuzzer estimates one distance between the seed and the whole target set. Now, this approach works well for direct fuzzing because you have usually a small target set, maybe 10, 20 targets, and usually close each other because maybe they belong to the same patch. So you can assume they are close in the code. However, when you start dealing with the huge target set that maybe have 10,000, 100,000 in some cases of target spread more or less randomly in the code, having a single distance from the seed to from the seed to the target set makes the seed not representative to reach all the targets altogether. The second challenge is that, as I said before, not all the targets, the target in our set are equally important. Previous work tried to apply static analysis, symbolic execution, or some heuristics in order to foresee before the fuzzing campaign what is interesting, what's not. But however, we observed that the current approaches might discard real bugs and thus leave false positive during the testing. To face and overcome these two challenges, we came up with FISHFUZZ. As I said, FISHFUZZ is a seed selection algorithm, and that's why I put this simplified version right on the right of the seed queue. This one, for the sake of time limitation, is a simplified version. And in the paper, you find a more complex one with more technical details. So for the time being, please stick with these slides. FISHFUZZ, as I said, divide the fuzzing campaign in two distinctive phases. One is called exploration, and then the other one is called exploitation. The goal of the exploration is to reach as many targets as possible. So in this phase, we don't expect to trigger bugs, but we expect to have a more fine-tuned seeds that can reach targets in the program. Okay. Once enough target has been reached, the fuzzer FISHFUZZ switch to the exploitation. In this phase, the seeds that already reached the target are even further mutated with the hope to exhibit a bug inside the fuzzer. All right. And in FISHFUZZ, we have two distinct contributions, one for the exploration phase and another one for the exploitation one. Now, let's talk about the first contribution. In FISHFUZZ, we propose a new seed target distance matrix that works at the call graph level. So in the slide, you see a simplified call graph where every block represents a function. And during the fuzzy campaign, we can mark and trace the execution path of a specific seed. So in this example, the execution path of the seed one is represented by the green blocks. And as you can see, the green blocks get closer to the target number one. Similarly, for the execution path of the seed number two, you see that there is another execution path, and in this case, the seed gets closer to T2 and to T3. This means that the fuzzer can infer that if you want to trigger T1, the seed 1 is more suitable, and similarly, if you want to trigger T2 and T3, the seed 2 is more suitable. This distance is calculated at runtime, and the seeds are selected in order to get closer to the specific target. The second contribution is a dynamic target ranking. Here, the intuition is simple, but quite concrete. The idea is that if you have a target that has been tested and traversed many times, probably the target doesn't hide a bug because it has been tested multiple times. On the contrary, if the target has been rarely tested, it's more likely to hide a bug. Now, this is not being traversed many times is not a formal proof that a bug is proof safe, but this gives an intuition, or at least a metric, that says that tests the fuzzer what targets deserve more priority and so more testing. So during the exploitation phase, the FISHFUZZ traces the visiting frequency for each target and try to hit the targets that has been traversed lesser time. In this way, we don't discard the targets a priori, but exhausted target they lose priority automatically during the fuzzing campaign. As I said, FISHFUZZ is a seed queue, is a queue cooling technique, and to demonstrate the flexibility of our approach, we present two prototypes, one based on EPFL, another based on EPFL++. And then we compare the bug capability of our approach against 8 fuzzers, others sanitizer guided and other two-stage fuzzers. And after our evaluation, we realized that FISHFUZZ managed to find roughly 3 times more unique bugs compared to the state-of-the-art, and we managed to find 56 new bugs in our benchmark. And among them, 38 got the CV assigned, also by Huawei. Sorry. So to conclude, FISHFUZZ has 3 main contributions. The first one is this queue culling algorithm that swings between exploration and exploitation, in order to reach and trigger as many targets as possible. The exploration part is implemented by relying on a new distance metric that finds more precise distance between seed and target. And finally, the dynamic target ranking allows us to automatically prioritize more promising target and discard exhausted one. The source code of our prototypes is available. Please check the link down below. The paper should be reachable through the QR code if I didn't mess up the QR code. And I'm here, the presentation is done. I'm happy to take your question. I'm in the conference if you want to approach me directly. Thanks.